we've been talking about, because it's kind of easier for us, I think, to describe visually these kinds of examples involving different types of input data. So, color images, color video, the kinds of three-dimensional scans, radiological scans that you're describing. But these tensors aren't just for storing the inputs, it's for storing the all of the weights and in the case of a neural network, the weights and the biases of the neural network. And it's also for storing the outputs, so our predictions. So these tensors are used to store data as well as model weights throughout the design, the training, and the deployment of our machine learning models, including our deep learning models. And so these tensors, this fundamental building block is seen throughout, and they can end up being within the deep learning models themselves. They can end up being many dimensional because, depending on, when you're talking about there like a 3D convolution, then you need to have high dimensional tensors representations inside the model in order to represent those operations. So I'm kind of hogging the mic here and describing what I kind of think is key here about these like fundamental building blocks. But so then when we go from these, if you kind of think about statically having a tensor of information, then how do we go, like, what's it like in PyTorch to then be doing operations, to go from having these static representations to being able to do something like being able to train a machine learning model?
Yeah. So you explained amazingly, like when you're building a deep learning model, you have each layer or each part of that model being a matrix or n-dimensional tensor stored to represent weights and biases that we call layers, basically. And there are many, many types of layers depending on what task we are trying to solve there. And in machine learning, we can't control the inputs and the outputs when it comes to the data set. So those are static representation of our data. That's what we collected, and there are many ways to collect the data. And that's something really crucial to do right before the algorithm comes into play. Now, we acknowledge, we can't control, we can't change the image itself or can't control the prediction what we want to achieve with that image. But we need to somehow learn or somehow make our algorithm reproduce these outputs on the newly comes data with which users might upload. And what can we change? Well, we can change those representations of layers inside of our layers. And we know now that those are just numbers in matrices stored for now. And that's what we tend to change. So how the process is changing is basically we take some images or whatever the data that we have at the input, we do operations with the neural network, depending on, of course, the layer type, the operation might change, and then we have some prediction. At the very beginning, those predictions will be really poor because the model itself doesn't really know what we want to achieve with it. So we make some predictions, and we say, okay, cool. So now that we have these predictions on top of it, let's see how right we are or how wrong we are, whatever the question you ask. And that's the loss function. That's the function that might tell us, okay, cool. So with this image, you were supposed to say it's a cat, but you said it's a dog. So sorry, but try again. And we are not doing that with a single image. We are doing with all the images in our data set, no matter how complex our task might be. Are we predicting the next word in a sequence, which is LLM, or are we predicting like what is the piece, what is the object on top of the image, or multiple objects? We still need somehow to determine whether or not we are correct, and that is a loss function. We do that across all the samples in our data training set, and once we do that, we take that information and perform partial derivatives on top of every single layer coming from the last one to the first one based on the loss function that is telling us, okay, so this is how wrong you are. Please correct yourself in some way. We are not right now, we are just telling it correct a small percentage, basically. And that's what we do. Now, after the single step, that's called an epoch, we have some corrections inside our network, inside those weights. We still have the static data, we still have the same images, same the output, but now those representations of matrices inside of each layer are a bit changed based on that wrong predictions that we made. So now let's try again and do basically that all over again. So we make predictions, we get again estimated how wrong we are, and we do now with the newly estimated wrongness how to correct the weights again. So we do that multiple times until we say, okay, now we are good enough. We are never perfect because we are working with really complex models, and not only that, but we have many samples, and every single sample in a data set might try to pull our weights in some direction, and we are making compromises all over again.
Nice. Yeah. So to summarize back what you just said, we have our static tensors, including the static tensors of our data set that we train on. And then we define some kind of loss function, some kind of way of quantifying where our model is wrong. Like you gave the example there of if it's a picture of a cat and our model predicts it's a dog, that's wrong. And so we use this loss function to quantify that wrongness. And then the magic and the power of a library like PyTorch or TensorFlow, frankly, is that then arbitrarily, regardless of what kind of deep learning model we designed, you talked about kinds of layers there. So you can have a small number of layers. You could have a shallow neural network with just like, the simplest kind of neural network layers, like a dense layer. And so you could have like just a single layer in your neural network, a single dense layer. Or you could have dozens of layers that are different kinds, convolutions, and dense layers, recurrent layers. There's all transformers. There's all these different kinds of ways that we can have our information interact within the neural network itself. But the point is that whether we're using PyTorch or we're using TensorFlow, the magic, the power of these libraries is that we can do partial derivative calculus from that loss function, that quantification of how we're wrong, and use partial derivatives to identify through all of these layers of our neural network, whether it's a small number or a large number, to be able to say, okay, how can I adjust this model weight so that in the future, I'm more likely to guess correctly that this is a cat instead of incorrectly that it's a dog.